Everybody. So I wanted to do an example. I called this displacement versus total distance, but really we're going to be talking a bit about the net change theorem, just some fundamental relationships between different kinds of quantities and what integrals are doing to them. So here's the setup. I'm given an object's acceleration in meters per second squared, and it is 5 sine t. So this means our t is in seconds. So this gives us the acceleration at each moment of time. And then we're also told that the object has an initial velocity at time equals 0 of -6 meters per second. Okay. And what our goal is to find, I guess I should have written this down. We want to find the displacement over the interval. Do this a little too thick. Maybe from 0 to 3, and also the total distance traveled over the same interval, right? So the difference between these two quantities, one, if I go for a walk and sometimes, if this is 0 and sometimes I step in one direction and sometimes I step in the other direction, displacement is how far am I when I finish from where I started. Total distance traveled would be how many steps did I take, right? If I took 3 this way and 4 back and then 2 back this way, right? I'll end up 1 step away from where I started, I guess in the positive direction, if I call that first direction positive. But on the other hand, I took 4, I forgot now what I said, 3 plus 4 plus 2, whatever numbers of steps I said, we add those up. That's how far I traveled, right? So, depending on what you're doing, you might be interested in either of those quantities, right? If you want to know where something is, right? If you're tracking an object, you don't care what it did in between, you just want to know where it ended up. On the other hand, if you're, keeping track of how much fuel it has used and you want to know its fuel efficiency, you'd want to know how much traveling it did in that time to get there. Okay, so we'll talk about these two ideas. So let's start with finding the displacement. So to find the displacement, right? Again, how far am I, or is the object from where it started? We could take, let's use S to be position. So we could just take its final position minus its initial position, right? Where it was in the beginning. So if it ends up, let's say there's some 0 point, well, I guess here we don't know. If there's some 0 point, and at the end it's 8 units away, then its displacement is 8 units. If it started at a point that we called 3 units, positive units, and it ends up 15 positive units, we'd have 15 minus 3, it's moved to 12 units away, right? On a number line, right? If it starts here at some number, I'll call n, and it finishes here, if these are our positions, the displacement will be m minus n, where it finished minus where it started, right? Well, in this case, again, I'm using S to be my position. This would be its position at, the final position is at t equals 3 seconds minus where it was in the beginning, right? So we want we need its position function, or at least something closely related to the position function. And if you look at this, if you think position at 3 minus position at 0, this should remind you of something. This would give us, or this would be given to us if we took the integral of the velocity function, right? Because the derivative of position is velocity. And so this position function is an antiderivative of the velocity function. There's some details in here I'll get to, but that's essentially the case, okay? So what that means is we can compute this if we can find our velocity function and then are able to integrate it. So How do we find our velocity function? Well, it's a very similar, there's a similar relationship here. If we integrate the acceleration function, we get the velocity function at least up to a constant, meaning we don't know exactly what it is, but we'll know what family of functions to look at, and then we can use our extra information to get that. So let's see why this makes sense. When we integrate, so I'm using taking, this is an antiderivative, but let's think if we were taking a definite integral of acceleration, we're adding up all these little pieces of acceleration times time, right? What does acceleration tell us? We write meters per second squared, but really what this is meters per second per second. So if you have an acceleration of 2 meters per second squared, it means 2 meters per second. It's telling you in each second, you gain 2 meters per second of velocity. So if you start out at 0 and your acceleration is 2 meters per second, after 1 second, you'll be traveling 2 meters per second. If that acceleration is constant and remains, after 2 seconds, you'll now be traveling 4 meters per second. And then another second goes by and you get to 6 meters per second. So you're gaining velocity at a rate of 2 meters per second every second. So when we add up all these little pieces of acceleration, what it tells us is how much total velocity did we gain, right, over that time period. Now, keep in mind, that doesn't tell us what our velocity is, because if I told you in the last 2 minutes, my vehicle added 10 miles per hour to its speed, you don't know how fast I'm going. You just know I'm going 10 miles per hour faster than when I started. You would need to know how fast I was going when I started. Notice we have that information. So we'll be able to find out how much our velocity has changed by. We'll know what the velocity was when we started, so we'll be able to get our actual velocity. So let's go ahead and do this. So I'm integrating my acceleration function, which was 5 sine of t. Right? If I want to use my properties of integrals, I can rewrite it this way. And now I'm looking at a fairly straightforward antiderivative. The antiderivative of sine of t, a function whose derivative is sine, is going to be negative cosine, right? It's easy to mix up that negative. We remember that there's a negative somewhere. It might be hard to remember which one. Most of us are a bit stronger at derivatives, especially in the beginning. So you can always take a derivative. Take a derivative of this negative cosine. The derivative of cosine is negative sine. You've got a negative sitting there at sine, and then our 5 sitting out there. We have to add our constant of integration, and then let's just write this in a more pleasing way like this. Okay, so there's the family of functions. Or another way I could say it is I have the form of my velocity function, but I don't know that constant. Okay, so what we do know, though, is that v of 0, which is negative 5 cosine of 0 plus whatever this constant is equal to negative 1. Cosine of 0 is 1. So this is negative 5 plus c equals negative 1, which gives me that c is equal to negative 6. Okay, so now I've got, let's do this, I've got v of t, I guess I'll keep working down. V of t is equal to negative 5 cosine of t minus 6. Okay, so there's step 1. We have our velocity function, right? And remember what we wanted to do, I wrote down here. I want to integrate this velocity function over this interval. This will give us the final position minus the initial position. So it'll tell us how much our position changed by. It will not tell us what we did in between, right? Our object could have done many, many things in between. So let's go ahead and do that. So we're going to integrate definite integral from 0 to 3 of negative 5 cosine of t minus 6 dt. This gives me -5 sine of t minus 6t. That's the antiderivative. And we're evaluating this from 0 to 3. Oh, I made an error. Pardon me. This is a quick change. I transposed on my notes. Sorry. Initial velocity is -6, which gives us c equals -1. I switched these up. I wrote -1 here. This should be 6. I just switched the given answer with the result I got. And this is a -1. Sorry about that. Let's change this really quick. Still pretty straightforward. This just changes to a 1. That's a 1. So we just get minus t. All right, sorry about that. So now we get -5 sine of 3 minus 3 minus -5 sine of 0 minus 0. So everything over here, sine of 0 is 0, 0 is 0, so that's all zeros. So we have this -5 sine of 3 minus 3, and that's something we would plug into a calculator or just leave as is. So I'll give the decimal approximation to this was -3.7056. Okay, so what does this tell me is that my object, in this case, the units would be meters because we had a velocity of meters per second. And so when we take this integral, we're multiplying meters per second times seconds, dt. We end up with a total displacement of -3.7056 meters. We ended up almost 4 meters in the negative direction from where we started. What we don't know is if we went really far away and came back, if we went slowly towards that and stopped when we got that far away. We could have done any combination of things, right? If this is my object and up is positive and down is negative, I know it started negative, maybe it went down, back up, back away, and ended up there. But it also could have gone down, up like this, and then ended up there, right? I can do this forever, coming up with different combinations of ways to end up at that place. So we don't know any of that. We just know where it ended up and how far it is from where it started. That is our displacement. How far is it displaced over that interval? Okay, so now we want to do something different. Now we want to get the total distance traveled. Let's come up here. Let's kind of reorganize, starting a new thing. So we've got, let's write down the information we have. A of t is 5 sine of t. We found v of t was equal to -5 cosine of t minus 1. Okay. So let's think about this v of t. This is our velocity. We know, for instance, when we start, we're moving backwards. A question we might ask ourselves is, over the interval 0 to 3, are we ever moving forwards? Right? That's if you're only ever moving in one direction. If I'm always moving forward, for instance, the displacement is also the total distance traveled. If I take 15 steps forward, I'll have traveled 15 steps and I'll be displaced by 15 steps. But if sometimes I move backwards and sometimes I move forwards, then the displacement and the total distance traveled won't match. So we want to know if this velocity function, which we know starts out at as negative, if it ever becomes positive. It's a continuous function, so to become positive, it would have to pass through 0. So what we could do is compute or find a t so that v of t equals 0. In other words, when is 5 cosine of t minus 1 equal to 0. This is when cosine of t is equal to, let's give this special t a little extra symbol. I'm going to call it t star. I don't feel like writing its number out a bunch. So cosine of t star is just whatever value makes this 0 is going to be equal to -1/5. So t star is the arc cosine of -1/5. And I can give this an approximation. I think it was like -0.7 or something. Arc cosine. Oh no, sorry, that couldn't be right. And then it's in the positive realm. It's we'll call it 1.77. All right, so approximately 1.77. Okay, so what does it tell us? It tells us after almost 2 seconds, our velocity is 0, right? And after that, it's going to be positive, right? I can sketch out a graph to see this. I know what cosine looks like, and we're looking at a negative. Let's see. If you remember your trigonometry, our midline is going to be at -1. We're going to go down as far as -6, up as far as 4. So we're starting down here. We're moving up for a while and then back down, right? It'll look something like this. And here's this t star, the place where this is equal to 0. And since it's smaller than 3, right? So 3 seconds somewhere out here, we know after t star, we're traveling in a positive direction. Over here, we're traveling in a negative direction, right? And what we learned last time is when we looked at how far we moved negative and then came back a little bit positive, the total distance, displacement was in the negative direction. So this area over here must be larger. So we need to integrate our velocity function again, except we no longer want to count this area as negative. We want to count this area as positive. So how do you make something positive? Well, we say absolute value, but let's be more careful about absolute value. When I write the absolute value of x, what I really mean is if x is positive or 0, I don't do anything to it. If x is negative, I multiply it by a negative. That's what the absolute value function does. That's one way we can think about it. Okay, so in this case, what does that mean? So this is, remember, my v of t function. I want to multiply v of t by a negative in this portion to get a graph of negative v of t, right? It looks funny to write negative and put it into positive, but it's because it started out negative. So over this first interval, I want to integrate over negative v of t. Over the second interval, I want to just integrate v of t, okay? So let's write this out. What does this look like? We're going to have, we want the integral from 0 to 3 of the absolute value of v of t dt. That's like our definition of displacement, taking the absolute value, or sorry, total distance. How it works out is I'm going to go 0 to t star, right? This is this number about 1.77. I'm just writing t star of negative v of t dt plus t star to 3 of v of t dt. All right. So what does this mean? So we've got v of t. Let's pull that back on for a second. -5 cosine of t minus 1. So I'm going to have 0 to t star of, I'm multiplying -5 cosine of t minus 1 times negative. So I'll get 5 cosine of t plus 1 dt plus t star to 3 of -5 cosine of t minus 1 dt. All right, so now we have two integrals to take care of. The antiderivative of 5 cosine of t plus 1 is 5 sine of t plus t, evaluated from 0 to t star, plus negative 5 sine of t minus t, evaluated from t star to 3. So now we simply plug and play. 5 sine of t star plus t star minus 5 sine of 0 plus 0. That's my first integral. The second one will look like plus negative 5 sine of 3 minus 3 minus negative 5 sine of t star minus t star. Okay, what do we end up with? Well, I've got 5 sine of t star plus t star. 5 sine of 0 is 0 plus 0 is 0, so this whole term goes away. And then I've got a minus 5 sine of 3 minus 3. And then look what happens here. When I distribute this negative, I get plus 5 sine of t star plus t star, right? So if I distribute this negative, this thing is exactly the same as this thing at the beginning. So now I've got 2 of those. And so there is our antiderivative, or there is our, sorry, our total distance traveled. Of course, let's get a decimal approximation to this. If we plug this in, I thought I had that answer. Maybe we'll do it really quick. So this is, at this point, a calculator problem. Pardon me, it'll just take 1 second. We have, what is t star? That is our arc cosine of negative 1/5. And then I'm just plugging that into this formula. So I've got 2 times 5 sine of t star plus t star minus 5 sine of 3 minus 3. I get 9.6367. 9.6367. Sorry about that. I thought I wrote it down, but it looks like I just stopped at this expression. Okay, so this would be meters again, right? So notice how different that is than the displacement. Right? What that tells me is that if we you know, eyeball these numbers here, we must have moved almost twice as far in the negative direction as where we ended up, and then moved back, right? Moved about, I don't know, 7 or 8 units in the negative direction, and then came back about 3, something like that. And so there's a whole much more distance that we didn't capture when we looked at the displacement, right? And that was evident in this picture, where we have the negative velocity here. We're moving in a negative direction for a while, and then we come back a little bit. My picture's not perfect, but we get the idea of what happened there. Let's do one more thing. Let's look at a graph of this a little bit better than mine. Let's see if I can grab this thing. I hope I can. There we go. So I have this graph ready here. Maybe I'll move over and get all this out of the way. Won't let me make it any bigger than that. That's all right. We can see that the graph here, right? This is a picture of our velocity function, and we can see that well, this isn't behaving nicely, but this is the negative part of the area, and then here is the positive. Sorry, the negative part. This is where velocity is negative, and then we see it becomes positive. And so that's a picture of the blue area remembers all of our, represents all of our movement in the negative direction. The red area represents all of our movement in the positive direction. Okay, I hope that helps. That's it for this one. Thanks, everybody. I will see you next time.